Let's start with the CU 2022 question. Here the question is, a transistor is operating in CE configuration. That means the transistor, the emitter will be common in input loop and the output loop. So this will be base, collector and emitter. So you can see the emitter is common in the input and output loop. This will be the input loop, this will be the output loop. So emitter is common. Okay, so this will be the CE configuration. Now they say a 560 ohm resistor is joined between the collector and the power supply. Okay, so here we have the resistance of 560 ohm. Voltage drop is 0.6 volt across it. That means if the current flow from this side, the voltage drop, this one will be 0.6 volt. Okay, if alpha is 0.97, then what is the value of base current IB? That means we need to calculate IB. Okay, so this current is IC, right? So we can write down IC equal to 0.6 volt divided by 560 ohm, right? From here, this one will be 1.07 milliamps. Okay, so now we have the IC. We know IC equal to beta into IB. Okay, and here we have alpha, right? So we know that beta equal to alpha divided by 1 minus alpha. Okay, so here alpha is 0.97, so beta will be 0.97 divided by 0.03, that is equal to 32.33. So the value of beta is 32.33. So if we put this one in this equation, then IB equal to 1.07 milliampere divided by 32.33. Okay, so then we will get 52.58 microamps. Okay, so this will be the answer. The value of IB will be 52.58 microampere. Okay, so let's go to the next question. The current gain of transistor in C configuration is 135. So C configuration means, I already told you in the last circuit, C configuration means the emitter will be common in the input loop and the output loop. So this will be VCC, VBB, base, collector and emitter. Okay, so here we have the IC and here will be IB. Here in the question, current gain of a transistor in C configuration is 135. That means IC by IB is the current gain, as IC is the output current here and IB is the input current. So current gain will be IC by IB. We call it beta equal to 135. Okay, and they ask here, calculate the emitter current if the collector current configuration is 49.3. That means here they mention IC equal to 49.3 milliampere. Okay, and they need IE. So we can write down IE equal to IB plus IC. As you can see here, this is IB and this is IC, right? And this one is the IE. So you can see that IB plus IC is equal to IE. If we just use a KCL, equal to IC divided by beta plus IC, I equal to IC common 1 plus 1 by beta. Okay, if we just put the value here, then we will get I equal to 49.3 milliampere multiplied by 1 plus 1 by 135 is equal to 49.66 milliampere. So this will be the value of I. So in the CE configuration, beta is 135 and the IC is 49.3. Then what is the value of IE? IE is 49.66 milliampere. So let's go to the next question. You can see this is a fixed bias circuit, right? and they ask here beta is 100 and assume VB is, this is VB, right, 0.6 volt, okay, and they provided VB saturation is 0.8 volt and VC saturation is 0.2 volt. Find in which region the transistor is operating. So let's assume the transistor is operating in the active region. Why? As for the IC equal to beta IB calculation, we assume that the transistor is in the active region. As if we just draw, this is IC and this is IB. How the plot looks like this, right? And this area is active region and this area is saturation region. We say that this slope, we call this slope as beta. That's why we write down IC equal to beta into IB. So IC equal to beta into IB, this expression only valid for the active region. For saturation region, we cannot write down IC equal to beta into IB, right? As you can see, it's already saturated. So let's assume this transistor work in the active region such that we can calculate the IC and IB with this relation, okay? And then just see what is the value of VCE, okay? If the value of VCE is less than 0.2 volt, that means the transistor is working in the saturation region, okay? If the value of VCE is greater than 0.2 volt, then we can say the transistor is operating in the active region, okay? So let's start. So if we just write down the KVL equation, we can write down 5 equal to, this current will be IB, okay? IB multiplied by 100K plus 0.6 volt, okay? So from here we can write down IB equal to 4.4 divided by 100 is equal to 44 microampere. IC will be beta into IB. So beta is 100. You can write down beta is 100 into 44 microampere. So this will be 4.4 milliampere. Then in this loop, if we use the KVL, we can write down 5 equal to IC multiplied by RC plus VCE. Okay. So from here, we know the value of IC, value of RC. If we just put that value, IC 4.4 milliampere multiplied by RC is 1.5 K plus VC. Okay. So from here you can see 4.4 multiplied by 1.5 would be how much? It will be 6.6. So from here we can get VC is minus 1.6 volt. Okay. That means what we assume here that the transistor is operating in the active region is wrong. Why? As you can see here, VC is less than 0.2 volt. Here we got the VC is minus 1.6 volt. Okay, so that means this minus 1.6 is less than 0.2 volt. Okay, that means this transistor work in the saturation region. Okay, so we cannot use IC equal to beta IB relation. Now we already know that the transistor is working in the saturation region. That means we need to use the VCE set and VB set value. So this VCE will be 0.2 volt VCE set and this VB will be 0.8 volt, right? Now let's calculate IB. We can write down 5 equal to IB into 100 plus 0.8. So IB equal to 42 microampere. Okay. Now we need to calculate the value of IC. We already know here the VC set is 0.2 volt, right? So if we implement the KCL here, then we will get 5 equal to IC into RC plus 0.2 volt. From here we can write down IC equal to 4.8 milliampere. So in the question, they just asking that the which region transistor is operating. So our answer will be only saturation region. Okay. But in some question, they ask you that just find out the Q point. So if they ask this question, Q point, and you find out the transistor is working in the saturation region, then you need to use this formula to calculate the IC and IB, and then you can write down the Q point is VCE, comma IC. What is the value of VCE? 0.2 volt. And what is the value of IC? 4.8 milliampere. Okay, so this will be your answer. So we already completed 2022 questions. This is 2021. In this question, they provided beta equal to 110. The question is same. Is the transistor operating in the saturation region? That means they just asking us in which region transistor is operating. So the process will be the same as the previous question. We will assume that transistor is working in the active region. That means IC equal to beta IB. Okay. And then we will find out the value of VCE. If the value of VCE is greater than 0.22 volt, as VCE set is 0.22, then this will be active region. If the value of VCE less than 0.22 volt, then this will be operating in the saturation region. Okay, so let's get started. If we just implement KVL in the input loop, then we can write down 5 equal to IB into 47 plus VBE plus IE into 2.2 kilo ohm, okay, equal to IB multiplied 47 plus VB is how much? VB is 0.7, right? In the normal time, VB is 0.7 plus I equal to, we can write down beta plus 1 into IB multiplied by 2.2. So just go step by step. So 5 equal to IB into 47 plus 0.7 plus beta is how much? Beta is 110. So this will be 111 multiplied by 2.2 into IB. Okay. So IB equal to 4.3 divided by 291.2, as 2.2 multiplied by 111 is 244.2, and plus 47, that will be 291.2. So the IB equal to 4.3 divided by 291.2 equal to 14.76 microampere. Okay, so the value of IB we get is 14.76 microampere. Now let's calculate IC. As we assume that transistor is working in the active region, that means we can say that IC equal to beta into IB. Okay, this is IC, this is IB, and this slope will be beta. So IC equal to beta into IB. Beta is how much? 110. And IC is how much? 14 point. IB is how much? 14.76 microampere. IC will be 1.623 milliampere. Now apply KVL in the output loop. We can write down 9 equal to IC into 3.3K, that means RC, plus VCE plus IE into 2.2 kilo ohm. Okay, so IC is 1.623 milliampere, 3.3 plus VCE plus 1.623 plus 14.76 into 10 to the power minus 3 into 2.2 equal to 9. Okay, so from here we can write down the value of VCE will be 0.041, right? You can see here in the question they provided the VCE value is 0.22 volt. That means the VCE is less than 0.22 VCE saturation. Okay, so if the value of Vc is less than the Vc saturation, then we can say that this transistor works in the saturation region. Okay, now if we need to calculate the value of the IB and IC, then what you need to do? You just need to take the input loop KVL with 0.85 volt as a VB and output loop KVL with the VC is at 0.22. Then you can easily get the value of IB and IC. So this is a very short question. They need the value of IE, where beta is 50 and IB is 20 microampere. So it's very easy. We know that IC equal to beta into IB. From here we can write down 50 multiplied by 20 microampere equal to 1 milliampere. Okay. So I equal to IC plus IB. It will be 1 milliampere plus IB is how much? 20 microampere. So this will be 1.002 milliampere. So I will be 1.002 milliampere. Okay. So if the IB value is 20 microampere and beta is 50, then I will be 1.002 milliampere. Okay. So now 2019 question. So they say common base current gain, right? So first we need to draw the common base circuit. So in the common base will be common, collector will be output, and emitter will be input, right? So the common base current gain, that means we can say the common base current gain. It will be how much? IC divided by IE, and we call this one as alpha. So IC by IE. So it say 0 alpha equal to 0.98. Okay, so that means beta will be alpha by 1 minus alpha. It will be 49. Okay, and the reverse saturation current ICBO is 12.5 microampere. They need the base current and the collector current when emitter current is 2 milliampere. That means IE is 2 milliamps and they need IC how much and IB equal to how much. IC equal to alpha into IE plus ICBO. Okay, so IC will be alpha how much? 0.98 multiplied by 2 milliampere plus ICBO will be 12.5 microampere. So IC will be 1.9725 milliampere. Okay, so we already have the value of IC and IE, right? So IC equal to 1.9725 milliampere and IE is 2 milliampere. Then what will be the value of IB? IB will be IE minus IC. So this will be 27.5 microamperes. So in this question, you can see for a fixed base current IB 20 microampere, if we change the value of VC from 7.5 volt to 12.5 volt, then IC will change from 3.5 milliampere to 3.7 milliampere, right? So they want the output resistance value. So if we see the output characteristics of a transistor, we know the curve will be like this for a fixed IB current, fixed base current, right? Suppose here we think this is the 20 microampere. That means for this 20 microampere, the curve will be like this. And they want the output resistance, that means the slope of this particular curve. Okay, so for the slope of this particular curve, what we can write down? This will be IC, it will be VC, right? So we can write down output resistance equal to delta VCE divided by delta IC. So 12.5 minus 7.5 divided by 3.7 minus 3.5. It will be 5 divided by 0.2. Then it will be how much? 25. Okay. From here we can write down the output resistance will be 25 kilo ohm. Why? As here in the numerator it will be voltage and the denominator is current, right? And the current here is milliampere. So we can write down 25 kilo ohm. So the output resistance R0 will be 25 kilo ohm. Okay. Now they need to know the value of beta. Okay. So the value of beta will be beta equal to what? Beta equal to, we know, IC by IB. Now they need the beta when VC is 12.5 volt, right? So for VC 12.5 volt, what is the value of IC? IC is 3.7 milliampere. Then we can write down 3.7 milliamps divided by 30 microampere. If we just divide this one, we will get 123.3. Okay, and they need the value of alpha. What is the relation between alpha and beta? Alpha equal to beta by 1 plus beta. So we can write down alpha will be 0.992. Okay, so this will be the answer. So go to the next question. So this is from CU 2016. In this question they provided beta is 100 and they want to know the transistor is operating in the cutoff, saturation or in the active region. That means we need to know the region of operation. Okay, so what we need to do? We just need to think that the transistor is operating in the active region. Why? As if so, then we can implement IC equal to beta into IB. That means, as I discussed in the last problem, this is active region and this is the saturation, right? In this region, we can follow IC equal to beta into IB. Then our calculation will be much easier, right? And we will calculate the value of VCE. If that value of VCE is less than VCE sat, then we will say transistor is operating in the saturation region. If the value of VCE is greater than VCE sat, then we will say that the transistor operating in the active region. Okay, so let's start it. What we need to do? Just apply KVL at the input loop. So we can write down 3 equal to 7 into IB plus 0.7 plus 0.5 beta plus 1 into IB. Why? As I equal to IC plus IB equal to beta plus 1 into IB. Okay, and why we say 0.7 VB? As we think that transistor operating in the active region, right? Here they say VB saturation is 0.8 volt, okay, but active region is 0.7 volt. So from here, what we will get 2.3 equal to 7 IB plus 50.5 into IB. From here, IB equal to 40 microampere. Okay, so what will be the value of IC? IC will be 40 microampere multiplied by 100. It will be 4 milliampere. Okay, now applying KVL at the output loop, what we will get? 10 equal to IC RC plus VCE plus IE into RE. Okay, then just apply the value, just put the value of IC 4 milliampere multiplied by 3 plus VCE plus IE, or you can write down that will be IB plus IC multiplied by 0.5. Okay, from here you can easily say VC is less than 0. Why? As this term will be 12, right? And if we move this part to the left hand side, then it will be minus 2, right? And here this part will be positive. So we can easily say VC is less than 0. Okay, so from this one we can say that this transistor is operating in the saturation region. Okay, as here they provided VC is at 0.2 volt, but we get VC is less than 0. So of course the transistor operating in the saturation region. So the first answer will be saturation region. Okay, now going to the next question. That means we need to calculate the V0 between collector and ground. That means we need to know this is the collector port. That means we will connect a voltmeter in the collector to ground. So we need to calculate the value of V0. Okay. So what will be the value of V0? We can write down V0 will be VCE plus IE into RE. We can write down this one. Or also we can write down 10 equal to IC into RC plus V0. Okay. From here you can write down 10 V0 equal to 10 minus IC into RC. We already have the value of RC. Okay, but we don't have the value of IC. The value we get for the IC, that one we get from the IC equal to beta IB relation. But that one only valid for the active region. But here you can see transistor operating in the saturation region. So we cannot use this formula. Okay, so we need to calculate IC again to calculate the value of V0. Okay, so let's start it. So now we already know this transistor is working in the saturation region. That means this potential will be 0.8 and this will be 0.2. That means VB is at and VC is at. Okay, so write down the KVL equation. 3 equal to 7 multiplied by IB plus 0.8 plus IE into 0.5. Here for the IE we cannot write beta plus 1 into IB. Why? As IC is not equal to beta IB. So we need to write down 3 equal to 7 IB plus 0.8 plus IB plus IC multiplied by 0.5. Okay, what do we write down? I equal to IB plus IC. This is universal truth. Okay, whatever the region of operation. So from here we can get 7.5 IB plus 0.5 IC equal to 2.2. Okay, so this will be equation 1. As you can see, this is equation 1 equation and 2 variables. So we need to get the another equation. So the another equation, what we will do, we will apply KVL at the output loop. So we will get 10 equal to IC into 3 plus VC. What is the value of VC? VC will be 0.2. As you can see, VC is at 0.2 plus IE into RE. IE will be IC plus IB into 0.5. So from here we can get 3 IC plus IC into 0.5 plus 0.5 into IB equal to 9.8. From here we can write down 3.5 IC plus 0.5 IB equal to 9.8. If we solve this two equation, then we will get the value of IB comma IC. Okay, and this is very easy. If we solve this equation, we will get the value of IB will be 107.6 microampere. You can easily do it. Okay, so just put this value in this one, equation 1, then we will get the value of IC. Put the values in the equation, and we will get IC will be 2.2 minus 7.5 into 107 10 to the power minus 3, that is in the micro, divided by 0.5. This will be 2.78 milliampere. Okay, now we already got the value of IC. Okay, so what we need to, for the V0 value, we already write down V0 will be 10 minus IC into RC. That will be 10 minus 3 multiplied by 2.78. Okay, it will be 1.66 volt. Okay, so this will be the value of V0. So V0 will be 1.66 volt. So this will be the answer for the question 2. So now we need to go for the third question, that is little bit different. Okay, so I just erase all of this thing. Now they are asking that we need to find out the value of Re such that transistor will be operating in the active region. That means the saturation, it is just in the limit. That means the voltage will be 0.2. Vc will be just 0.0020000001, or you can write down 0.2. Okay, and we can also apply IC equal to beta into IB. With these equations, we need to find out the value of Re. Okay, so let's calculate. If we apply KVL at the input loop, we can write down 3 equal to 7IB plus 0.8 plus RE into I. It will be 7IB plus 0.8 plus beta plus 1 into IB into RE. Why beta plus 1 into IB? As we can write down IC equal to beta into IB. So IE equal to beta plus 1 into IB. Okay. So this will be 7IB plus 101 IB into RE equal to 2.3. So this will be equation 1. Okay, so we need to find out the another equation to solve this equation. Okay, so 10 equal to 3 into IC plus 0.2 plus beta plus 1 into IE into RE. Okay, from here we will get 101 I, this will be IB, 101 IB into RE plus 3 IC equal to 9.8. Okay, so if we just solve this equation, we will easily get the value of Re. Okay, so just replace this value. Okay, so you can write down 7 IB plus 9.8 minus 3 IC equal to 2.3. Okay, 7 IB plus 9.8 minus 3 into beta into IB equal to 2.3. Okay, from here, if we just put 9.8 in this side, then we can write down 7 IB minus 300 IB equal to 2.3 minus 9.8. Okay, from here we can get minus 293 IB equal to minus 7.5. Okay, by solving this one, we will get the value of IB will be 25.5 microampere. Okay, now if we put the value of IB in equation 1, then we will get the value of RE. So what will be the value of RE? RE, we will write down 2.3 minus 7 into 25 to 10 to the power minus 3. Okay, then the data will be in the kilo ohm, divided by 101 into 2.5 into 10 to the power minus 3 is equal to, it will be 0.820 kilo ohm. That means 820 ohm. Okay, that means when the value of Re is 820 ohm at that time that this transistor will just switch from saturation to active region. Okay, so the first answer will be saturation, second answer will be 1.66 volt V0, and the third answer will be Re equal to 820 ohm. Okay, now just go to the simulation and I will show you these answers. Okay, though I cannot show you VB is at 0.8 and VC is at 0.2, but I can show you the value is close to our result. Okay, so let's go to the simulation. So this is the circuit given in the question. Okay, the input voltage 3 volt, VCC 10 volt, and this one is the V0. So we need to find out the value of V0 in the second question. First we need to know that this transistor is operating in the which region. Okay, so we just connect this one in the VC. Now let's simulate this circuit. Here you can see this transistor, for this transistor is 98.9 the VC. That means in the question they provided VC is at 0.2 volt, that means 200 millivolt, right? So that means this transistor is operating in the saturation region. Okay, so this question is clear. As in from our calculation also, we also get the transistor working in the saturation region, as we get VC equal to negative. Why? As we think that IC equal to beta into IB. Okay, so the first question is complete. Let's go to the second question. The second question, we already assume that transistor is operating in the saturation region, and we consider VC is at 0.2 and VB is at 0.8, and we calculate the value of IB and IC, and from then we calculate the value of V0. Okay, so let's disconnect this one and connect to the ground and the collector terminal, that means V0. Now at that time we got the value is around 1.6, right? Now you can see here is 1.56. Why 1.56? As you can see here, this voltage, if you see, this voltage is 2.21 at the base terminal, and at the collector terminal this voltage is 1.46, right? So that means it's less than 0.8. But in our calculation, we consider VB sat will be 0.8 and we consider VC sat is 0.2. But here also you can see the VC sat is around 98 millivolt, right? So for this transistor, as the VC sat VB sat is different, so that's why the output voltage V0 is little bit different. But you can see it's very close to V0. Again, you can see in our calculation we get the IB current is 107 microampere. Here is 130 microampere. Why? As VB sat is little bit different. Okay, this is answer for the second question. Now go to the third question. For the third question, what they need to know the transistor should be operating in the active region, right? That means this voltage, V voltage, the VC voltage should be 0.2, and we need to find out the value of RE. So what we will do? We will change the value of RE and we will check the value should be 0.2. At that time we will stop. Okay, so just simulate. Now the value of VC is 98 millivolt, that means it's still in the saturation. So we will change the value. First, what the data we get is around 820, right? So we will go around 800. Now you can see it's already 235 millivolt. Okay, so our result is very close to this one. Okay, so in this software we cannot set the VB is at 0.8 and VC is at 0.2. Okay, that's why it's not exactly match, but we saw that our result and the simulation result is very close to each other. Okay, thank you.
Thank you for watching my video, and share this concept with your friend, and like and subscribe my YouTube channel. Thank you.